Now we'll be looking at how we can create a random generator based off a popular bit of shader code found online. Doing a quick internet search for random GLSL function gives this Stack Overflow result as the top item. GLSL stands for OpenGL Shading Language, which is a programming language designed for programming vertex and pixel shaders. Unreal's materials ultimately get turned into this code under the hood, so we can adapt it and implement this function in Unreal's material editor. Let's click on this link and scroll down to the top answer to this question. I'm going to select this code and copy it, and then over in Unreal I'm going to create a new material function that we will be recreating this function in. I'm just finding it in the menu, and I will call this mf_random2. Let's dive inside, and I'll set up my usual editing layout, which is to remove the stats window, switch to a left view, change to lit mode, and set the preview mesh to a plane. I'm going to break down how this function works, so I'll paste it into a comment block by hitting C and Ctrl V, so we can refer to this in the editor. Now let's break it down. The trick is to not look at the whole thing, but start by looking at just one part, starting from the inside and working our way outward. The bit we will start with is just to look at this vector in the middle. It's just a simple 2D vector that points in a particular direction. Next, we need to keep in mind that because UVs are 2D points, we can consider the whole UV space as an infinite bunch of points. Then we do an operation called the dot product. There are a few ways to interpret what the dot product does mathematically, but the useful way of interpreting it here is that it performs a projection from the UV points onto the line defined by the vector. The result is a single scalar or floating point value, which is where along that vector the UV point landed. If we twist this graph over on its side, then it's easier to see where the UVs land on the vector, and that they flatten down to a one-dimensional number, which is the position along that line. We are already familiar with the sine function and how it results in this wave-like shape, where the input is a one-dimensional number and the output is the height of the sine wave. If we take the result of the dot product and feed it into the sine function, we get back a value that is the sine wave spread in the direction of the vector. Also, the rate at which the sine function oscillates is actually a lot quicker because of the magnitude of the original vector. And now we can turn the graph back the right way up to see how the sine wave propagates in the vector's direction. The wave is actually oscillating so quickly that inaccuracies in floating point numbers start to create noise. The final trick to getting the noise is to multiply it by some huge number so the range varies wildly, and then take the fractional part of that to make every whole number wrap around into the 0 to 1 range. So the theory wasn't that hard. Now let's actually create it. We need to start by setting up the inputs to the function, which is just the 2D UVs. We'll connect up some default texture coordinates and set them as the preview value. Then we need to create a constant 2D vector, which is the constant from the function. You can hold 2 on the keyboard and click in the editor to place one down, and I'll enter these into the RNG component fields. Next we need to perform a dot product between the UVs and the vector. So create a dot product node and plug in the UVs to one slot, and then the vector into the other. Plugging this into the result, we get to see the result of the projection of the UVs onto the vector line, which very quickly goes above 1, which explains why it's pure white. Next we need to plug this into the sine function to get the oscillating sine wave in the direction of the constant vector. So plug the dot product result into the sine node input plug, and we can see that the result is indeed the sine wave we were expecting. The next step is that we need to multiply by this huge number. So create a multiply node, connect up the sine output to it, then create a constant node, set the constant to the value from the function, and plug it directly into the multiplier. The final step is that we need to take this huge range from the oscillating sine wave and restrict it to the range 0 to 1. Create a frac node and connect it up between the multiplier and the result. By doing this, massive values that are varying per pixel between around -43,000 and +43,000 get wrapped into the 0 to 1 range and appear as noise. Now we have our final random 2D generator, which gives us a random value between 0 and 1 for each different UV input. Now all we need to do is save this function, as we'll be using this later.